So I need to share the screen. Okay, so is this visible? Hope so.
Yes.
Okay, so I wanted to get back to talking about the Tarski-Seidenberg theorem, and unfortunately, I really had to finish two papers this week, so the time I was going to spend trying to understand what these guys had done never popped up. So I'm going to talk a little bit, and partly because it's interesting and partly because it's something that people should know about. If you're not familiar with this, I'm going to start with a complete diversion, which is the problem of sums of two rational cubes. So there's the following, I could say a classical question, but there are maybe not Aleph naught, but close to Aleph naught classical questions that have to do with sums of cubes. Very often you want to know what integers can be represented, for example, as 4 integer cubes. But another problem is to ask about representing integers as the sum of 2 rational cubes. So for example, 6 is a sum of 2 rational cubes, and the cubes can be positive or negative, but here 6 is a sum of 2 positive cubes, and 13 is a sum of 2 cubes. And you might try, if you want, to take a random integer and write it as a sum of 2 cubes. It is a extremely hard problem, it seems. I mean, hard means no one's figured out how to do it, but seems to be a very hard problem. If you actually start looking for integers which are sums of 2 rational cubes, these are the first ones on the list. So not 3 or 4 or 5 and so forth, and those things are provable, but these are the first integers that are sums of 2 cubes. Actually, I didn't count how many there are. Let me just see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So roughly 2/3 or more or less, but not everyone. And you might ask, what integers are sums of 2 rational cubes? That's quite hard. You might ask, what proportion of the integers are sums of 2 rational cubes? Or what is the density of these integers? And there is a conjecture. I have no idea where the conjecture comes from. I mean, I do slightly, but there is a conjecture that half with density, half of the integers, density a half of integers are sums of 2 rational cubes.
So
if you can
sorry
prove
for
this,
for disturbing you. Sorry for disturbing you. So those that don't appear in the list, it was, for instance, 5. Was it proved that 5 cannot be represented as a sum of 2 cubes?
yes.
Okay.
So there is a conjecture that the density is a half. Now, in classical number theory, if you have a problem involving cubes that you can't solve,
whose conjecture is this?
I don't know.
Where have you seen it? I mean, it's just folklore.
I'm about to give some references.
Okay.
Okay. But in general, if there's a problem involving cubes that you don't know how to solve, you assume that it somehow is connected with elliptic curves, and so there has to be a little bit of arithmetic geometry that's involved, and that's where this conjecture comes from. I mean, it's in any case, this is the conjecture, and the remarkable thing is progress in this. So there is a very new article on Quanta magazine. Erica Klarich is a very good writer for Quanta. mathematical trio advances century-old number theory problem. So three guys, here they are, Apogee, Bargava, and Schnittman, wrote a paper, it's on archive, this is the reference, about the frequency of integers that are sums of two rational cubes. And what they found was an upper and a lower bound. So this is their theorem, that the density of integers that can be represented as a sum of two rational cubes is between 2/21 and 5/6. So of course, if you're interested, a half is in between. So the conjecture is still viable, but this is a big deal. I mean, in the sense that this is a classical problem on which there had been essentially no progress. And in her sort of survey piece, Klarich writes that essentially COVID is responsible for this, because Alpogi and Schnittman is in Jerusalem, and I'm not sure where this guy is, but they both independently got COVID, and they were stuck at home. And evidently, they had been Zooming once a week or so with Bargava, and Bargava said, well, since you guys are sitting at home with COVID, maybe we should Zoom, like 2 or 3 or 4 times a week. So, so they did, and this was the result. So I just bring this to your attention from the point of view of general number theoretical culture. Okay. That's the beginning and the end of this diversion. So what I want to talk about, hopefully in the next week or so, I'll figure out a little bit more about what is involved, is a theorem of Tarski and Seidenberg. So Tarski, Teitelbaum really, but then at some point he felt it was safer to change his name, proved a theorem in 1930 in Poland. And somehow it became difficult to publish too much in the early 30s in Poland. And so his manuscript existed, but it wasn't published. It was published 20 years later, reprinted in a paper by the Rand Corporation. So the foundational papers are this paper of Tarski, a decision method for elementary algebra and geometry, which was written in 1930 and published, but really republished, reprinted by the Rand Corporation. By that time, Tarski was at Berkeley, and his colleague Seidenberg gave a new proof and somewhat more general result in a paper called A New Decision Method for Elementary Algebra, which was published in the Annals. And both of these papers I included in my email that I sent out yesterday, if you're interested. In fact, I hope someone is interested, because I hope someone will read some of this and be willing to talk about it and make it easier for me. But in any case, in principle, the papers are now easily accessible to you. So what is this about? A decision method for elementary algebra and geometry. Now, everyone knows there's no decision method for elementary number theory, even for polynomials. This was Hilbert's 10th problem. If you take a polynomial with integer coefficients and you don't even ask for the solutions, you just want to know if the polynomial has a solution in integers, that's an undecidable, unsolvable problem. But here we're talking not about integers, but real numbers. So this is, so Seidenberg starts off by saying, what is Tarski's problem? Tarski has given a decision method for elementary algebra. In essence, this comes to giving an algorithm for deciding if a given set of polynomial inequalities has a solution.
There's something, by the way, if you're talking about real numbers versus rational or integer, you can't actually give as an input a real number. You can only give, real rational numbers, integers, maybe algebraic numbers. I mean, so the input will be actually, let's say, integers or something like that, and you'll be asking for a solution in rationals.
Right.
In
But
real time.
but you also have the following possibility. You have a polynomial, and let's say somewhere on the interval from 0 to 1, it's negative. So you can prove that. And somewhere else on the interval from 0 to 1, it's positive. And then you can say without any rational approximations or that polynomial does have a 0. It does have a solution in the interval between 0 and 1. So you can give an affirmative answer, unambiguous, to the decision problem, and you don't have to give a solution. The problem is that the question you want to answer is, given a polynomial equation or a polynomial inequality, where your polynomial has real coefficients.
Well, that's the thing. You can't specify a real number in general.
I understand that, but that's irrelevant to the decision problem. The decision problem doesn't ask for a solution. It doesn't ask for an approximation to a solution.
I'm just talking about the
asks
input.
for a yes or no answer to the question, does this set of inequalities have a solution?
But to ask the question, you can only ask a precise question if your input is something precise. You can't give an arbitrary real number in finite time. Tarski's talking about situations where you have precise questions to which you're asking for answers. The only way to specify a real number is with some finite amount of information. Most real numbers can't be specified that way.
Okay. Now, in Seidenberg's paper, the question is reduced to a very special problem. You want to know if a polynomial in just 2 variables with rational coefficients has a real solution. And again, you might want the next few minutes while I'm talking to shut off the sound and see if you can figure out whether or not a polynomial in 2 variables has a solution or not. I don't know. Doesn't seem that hard, maybe. I don't know. Okay. So what Tarski is considering are what are called first order formulas over the reals. So what is not a formula is to say, here's a polynomial, it doesn't have an integer solution. That is not the kind of question that is under discussion, right? There's no way to specify integers. Polynomial inequality. So this is the sort of thing that Tarski is considering. We have a polynomial in n variables, n is arbitrary and with real coefficients. And we're interested in decision problems. So a simple decision problem might be, does this inequality have a real solution? Strict inequality. Or does this equation have a solution? All right, that is the type of problem Tarski is interested in. And we looked at greater than and equal. In fact, but of course you have other, equality and inequality signs. But for example, inequality, but you can reduce everything to greater than or equal in lots of different ways. So this is, I don't know what this is, pre-calculus maybe, but to say that f different from 0 is the same as saying f squared is greater than 0. So you can replace an unequal sign with a greater than sign. Or, well, this one's clear. If f is less than 0, that's the same as saying minus f is greater than 0. F greater than or equal to 0. So f's a polynomial in n variables. This is now a polynomial in n plus 1 variables. So f is greater than or equal to 0 if and only if this equality, this equation has a solution. And less than or equal, well, That's the same as saying f plus z squared equals 0. So what all this says is, if you have any finite set of polynomial inequalities and polynomial equations, you can reduce it to a finite set of strictly greater than inequalities and equalities. But in fact, you can also get rid of the greater than sign, because to say f is greater than 0 is equivalent to saying you can solve the equation fz squared equals 1, or if you like, fz squared minus 1 equals 0. So you can reduce every equation, every inequality or inequality to an equation. And every finite set of polynomial inequalities and polynomial equations is equivalent to a finite set of polynomial equations, which is simply one polynomial equals 0, another polynomial equals 0, and so forth. And if you don't like dealing with a finite number of equations, just take the sum of the squares. So each of these individually being 0 is equivalent to this one polynomial being 0. So the decision problem in elementary algebra over the reals, we can say, this is not really advanced perhaps, is equivalent to the problem of determining if a hypersurface in Rn defined by a single polynomial, this should be an R and not a Q, contains a point with real coordinates. If there's something on the if you can decide whether or not a hypersurface contains a point, you have solved the decision problem for algebra and geometry. Okay. Any questions about that? Comments? Now, what's involved in the Tarski-Seidenberg work are something like two equivalent statements. One is reduction of the number of variables.
In the previous, a couple slides back, you said that it gets reduced to the case of rational coefficients and two variables. Is that also a situation where the rational is replaced with the real? Like what you said in the previous.
Sorry, is there a question?
Yes, sorry.
Yeah.
You said in a few slides ago that it could be reduced to the question of does a polynomial with rational coefficients and two variables have a real solution?
Right.
That rational have also been replaced with a real?
No. So that is actually the key step in Seidenberg's proof. Seidenberg has a different proof from Tarski. So Seidenberg does a certain amount of work and reduces it to that question, which is exactly as I stated it.
Okay.
But I'm more interested in the original work of Tarski, and what's involved are what is sometimes called quantifier elimination or reduction of the number of variables. So there's the following theorem that says the following. Suppose there is an algorithm which, so again, the original problem, most simply stated original problem is you have a finite number of polynomial equations and inequalities. And the question is there a sum, does there exist? You don't have to find it. Yes or no, do these equations and inequalities have a common solution? Right? Decide that, yes or no. That is the decision problem. And so if you have a finite system of polynomial inequalities and equations in n variables, that's what this S is. There is an algorithm which, starting with this finite set of inequalities and equations, produces not one, but a finite set of finite systems. So here I have one system in n variables. I will get out a certain finite number of systems of inequalities and equations in n-1 variables, such that your original system has a real solution if and only if at least one of these derived systems has a solution. So I can reduce the number of variables. Right? Now, here is the standard example that you learn in elementary school of quantifier reduction. You have the following problem. We have a system which consists of one equation and one variable. And we want to know, does this equation have a solution? And we learned that there are three systems of equations in one fewer variable. Well, if you start with one variable, that means we have no variables, such that the first system is A1 different from 0 and the discriminant is non-negative. In the second system, A is 0, but B is non-zero. So it's just a linear equation. And in the third system, A, B, and C are 0. So if any of these three statements is true, then this equation has a solution. And if not, not. Right? So here I want to decide, does this equation have a real solution? I've eliminated the variable A, B, and C. You can think of these are parameters, but they don't vary. They're given with the system. So this is an example of eliminating a variable or reducing a quantifier. Okay. Oh, so this original system has a real solution if and only if at least one of these statements is true. That's okay. Just as in algebraic geometry, you look at solutions of polynomial equations, and an algebraic set or a variety is the set of common solutions of a set of polynomials. If you enlarge what you consider and think of and have polynomial equations, but also polynomial inequalities and n variables, the set of common solutions is what is called a semi-algebraic set. And or if you take a system, what's called a basic semi-algebraic set, and from your collection of basic semi-algebraic sets, you look at the Boolean algebra they generate. You take unions, intersections, complements, and so forth, and those things are called algebraic semi-algebraic sets. And another part of the, it's likely not in the same language, but of this Tarski-Seidenberg work, is a projection theorem. If you let pi be the projection of Rn to Rn minus 1, by projecting onto the first n-1 coordinates, then the projection of a semi-algebraic set in Rn is a semi-algebraic set in Rn minus 1. Okay. By the way, this is kind of familiar to us in a different context, because when I was talking about the Farkas theorem and some things in convexity, we proved that if you have a polyhedron, which means, and you project it onto a lower dimensional space, the projection of a polyhedron is a polyhedron, and that is a fundamental fact in convexity. Okay, so, all right, now, the key tool, especially in Tarski's work, is Sturms Theorem. And I spoke about this maybe 6 months ago. But of course, I mean, the things that we've spoken about 6 years ago or even further back, and one can't assume that everyone has been around, even alive. So, and also so Tarski uses Sturms Theorem, and he uses then a generalization of Sturms Theorem. But what I want to do in the remaining little bit of my talk is just review the proof of Sturms Theorem, because first, I don't really understand it, even though I can, explain it with my eyes closed. but also it is the crux of everything that Tarski does, right? I mean, in some sense, this whole decision problem for algebra over the reals is are a set of corollaries of Sturm's theorem. By the way, and I'm following van der Waerden, which the more I look at van der Waerden's algebra book, the greater my appreciation of van der Waerden becomes. I mean, it's in a certain sense, and Lang himself admits this, Lang's standard book, which is twice as large as the 2 volumes of van der Waerden, is basically van der Waerden with a few things added, but it basically follows the same topics in the same order. And
I think, Kevin, I think that van der Waerden's book is based on lectures of M.E. Noether.
yeah, Noether and Artin, and he says that in his book. But you still, the author still sort of picks and chooses what to write and how to write it, and I would say neither Artin nor Noether ever did. But I mean, van der Waerden, I mean, this book was a classic, and I would say justifiably so. You might not like his political history, but he did write a great book. In fact, he wrote a lot of great books. In fact, he actually is really miraculous. If you look at just the books that he's written on the subjects, there are things on, history of mathematics. He has a great book on the history of early mathematics, on quantum mechanics, on mathematical statistics, on algebraic geometry. He was a person of vast erudition. Whether he was a Nazi or not is under discussion. He certainly seemed to have no problem spending World War II in Germany. He was Dutch, but that's where he spent his time. But this is a great book. And I remember when I was a graduate student, Stanley Tannenbaum told me I should really learn van der Waerden, and I didn't, but I should have listened to him. Instead, everyone was reading Lang then, right? And but there is the dictum of whoever it was, Eisenstein or someone, read the masters, not their pupils. So, and this is van der Waerden really is a master. And even in 1931, when we turn to the computation of the real roots of a polynomial, by computation we mean, as Moshe said earlier, in accordance with the definition of real numbers, an arbitrarily close approximation by rational numbers. Right? So that is I think that is a somewhat sophisticated notion from 100 years ago. So the proof of Sturm's theorem only uses one elementary fact, which I mentioned earlier, which van der Waerden calls the Weierstrass-Nullstellensatz. So f is a real valued function of a real variable. If it's continuous on an interval and negative at the left-hand endpoint and positive at the right-hand endpoint, then it's 0 somewhere in between. Okay, so you teach your students this in calculus without proof. But, van der Waerden, of course, constructs the real numbers and gives a nice proof. And what we use in Sturm's theorem is a slightly modified division algorithm for polynomials. So, so if you take u and v polynomials where v is different from 0, and you're going to divide u by v, you get a quotient and a remainder. And the modification is we write as a remainder, we use the negative of the traditional remainder. So there are unique polynomials q and r such that u is qv minus r, not plus, where the remainder polynomial is either 0. We say the 0 polynomial has no defined degree, or it has a degree, but the degree is strictly less than what you're dividing by. So that's the modified division algorithm. And we use a modified Euclidean algorithm applied to a polynomial f of x with real coefficients. So we let f of x be f0 and f1 be the derivative of f. So we start with F0 and F1, and we're basically going to calculate the greatest common divisor of F and F prime using a Euclidean algorithm. So you take, and what is that? Like you take a number, divide it, and you get a remainder. And then you take what you're dividing by and divide it by the remainder, and you get a new remainder, and you continue. So F0 divided by F1 has a remainder minus F2. F1 divided by F2 has a remainder minus F3, and so forth. And as you go through this Euclidean algorithm step by step, the degrees of the remainders are strictly decreasing. And somewhere they teach you, or they brainwash you into thinking that a strictly decreasing sequence of non-negative integers eventually has to stop. So it stops when you have no remainder. The remainder is 0. So if we iterate this this division algorithm, after r steps, we get to fr minus 1 is divisible by fr with no remainder. So the greatest common divisor of the polynomial f and its derivative f prime is this f sub r of x. And what is called the Sturm sequence of f of x is this sequence of polynomials, r plus 1 polynomials. F0 is the original f, f1 is f prime, the derivative, down to fr. So that is the Sturm sequence. And Sturm's theorem says the following. So take any real number lambda. So if you take your Sturm sequence and evaluate each of the polynomials as lambda, this is a sequence of real numbers. And the Sturm variation function counts the number of sign changes in this sequence. So as you go from left to right, you ignore any zeros. And whenever you have a positive number followed by a negative, or a negative followed by a positive, that is a sign change. So you count the number of sign changes. And Sturm's theorem says, if you have a non-zero polynomial and you take this Sturm sequence, if you have numbers a and b, so the idea is we want to know how many roots the polynomial has in an interval between a and b. So a is less than b, and you choose them so you don't have a root at either a and b. So f of a is non-zero and f of b is non-zero. Then the number of roots of f of x, not counting multiplicity. You know, you might remember in Descartes' theorem and other theorems we've talked about, we're somehow counting the number of roots with multiplicity. Sturm's theorem gives us the number of roots not counting multiplicity. You simply evaluate the Sturm sequence at A, the number of sign changes, or sign variations, that's I guess what the V stands for, or the number of sign variations plus or minus sign variations at B, and the difference is the number of roots between A and B, which by the way tells you somehow that as you move from left to right, so if you look at this function, S of f of lambda, as you move from left to right, it's always not increasing, right? Because if you had like this was equal to 3 and this was equal to 5, you would get minus 2 roots, which doesn't make any sense. So this is in fact a decreasing or non-increasing function as lambda goes from minus infinity to plus infinity. So that's Sturm's theorem. And
a quick definition, how's the Sturm variation function defined if one of the polynomials evaluated at lambda gives 0? So if you have like -0, positive, are there 2 sign variations or only 1?
I'm sorry, I don't understand what you mean. If one of these is 0,
One of these is 0 at lambda.
okay,
How's-
you erase it, you cross it off, you don't count it.
You don't count. You don't define this when lambda.
So if
when-
this is positive and this is 0, that is not a sign variation.
okay.
That
And
is, if you like, do you have this sequence of numbers and erase all the zeros? So you only have positive and negative numbers. And then you count the sign variations. You completely ignore the zeros. Right? If you had plus, 0, minus, that's 1 sign variation. Okay. Okay. And I will say, even though I've looked at this many times, it's not obvious to me. I mean, I know the proof, but I cannot say why this should even be true. Right? I mean, I don't know. I find it kind of mysterious. And the proof, I mean, I have seen people give basically this proof and write it down in 2 paragraphs. But the 2 paragraphs it's almost as if this, and then of course this, and the following is obvious, and we proved the theorem. So anyway, so that's here. I'm going to now sketch the proof. It's actually a complete proof, but so we have f of x. So suppose lambda is a root of f of x of multiplicity L. So if L is at least, if this is not a simple 0, a simple root, if lambda is a root of multiplicity at least 2, then f of x, you can always write it as x minus lambda to the L times g of x, where g of lambda is different from 0. So if you differentiate this and you took calc 1, you get that f1 of x is x minus lambda to the L minus 1 times this, right? This is just calculus. And this part in the parentheses is not 0 at lambda. So if f has a root of multiplicity L, then f prime has the same root of multiplicity L minus 1. But now if you go back and look at this Euclidean algorithm, so x minus lambda to the L minus 1 divides f, which is f naught, and f1, and f prime, which is f1. So if it divides f naught and f1, it divides f2. But if it divides f1 and f2, it divides f3. So in fact, this factor of x minus lambda to the L minus 1 divides every polynomial in the Sturm sequence. And so x minus lambda to the L minus 1 is a common divisor of f naught and f1. But it doesn't divide f1, but it divides all of the terms in that Sturm sequence, and particularly the last one. So I can, if I want, take all the polynomials in the Sturm sequence and divide it by fr, by this fr of x, this last term. And now lambda will be a simple root of f naught over fr. And by the same argument, of course, every root of f of x is a simple root of this. So f naught of x, again, let me go back and show. So fr of x, this is the greatest common divisor of f and f prime, or f naught and f1. So if I divide by, and fr divides all of the f naught, f1, f2, and so forth, divide by fr of x, then f naught of x has only simple zeros. So lambda is a simple root of this, and every root of f of x is a simple root. Okay. So this is what I just said. Take every one of the terms of the Sturm sequence, fi of x, and divide it by fr, and we get a new sequence of polynomials and a new sequence of equations. Again, I have to keep going back, I guess. I'm dividing by fr, so these q1s don't change, right? Just because every one of these f polynomials is divisible by fr. So I have this sequence of equations, which is not the Euclidean algorithm. It is simply a sequence of equations, and this gr of x is 1, because gr is fr divided by fr. So this gr is 1. Now, for any number that is not a root of fr of x, the number of sign changes in this sequence of the sequence of g's is the same as the number of sign changes in this Sturm sequence f, because when you divide by fr, you don't change any of the, you either, so if fr of lambda is positive, you're dividing everything by a positive number. Or if it's negative, you're dividing everything by a negative number. But the number of sign changes is invariant. It doesn't vary. So if you look at the sign changes in this sequence, is exactly the sign changes in the original Sturm sequence. So it's enough to study the sign changes in this sort of modified Sturm sequence. And we can make a couple of observations. So suppose for some lambda between A and B, two consecutive polynomials, Gj minus 1 and Gj, had zeros at lambda. But this means, just from that sequence of sort of like recursion relations, that Gi of lambda is 0 for all I from j minus 1 up to r. So in particular, Jr of lambda is 0, but Gr is the constant function 1, which is absurd, which means if we look at the sequence G0, G1, and so forth, there can be lots of these polynomials have zeros, but no two consecutive polynomials have a common root. So we have this sequence of polynomials. A polynomial has only finitely many roots, so that lambda be the finite set of all roots of any of these polynomials. That is, you let lambda be the set of all numbers d such that Gi of d is 0 for some I. So this set lambda partitions our interval from A to B into a finite number of subintervals. And if you are in one of these subintervals between zeros of one of these polynomials, then in that subinterval, none of the GIs vanishes, which means these GI polynomials are either always positive or always negative. Because if it was positive somewhere and negative somewhere else, by the Weierstrass-Nostalensatz, the polynomial would have a 0 in the middle. So this set lambda partitions the interval from A to B into subintervals. And in each of these subintervals, I mean the open subintervals, these polynomials are all non-zero for all I. And so they have the same sign in each of those subintervals. And so this variation of signs function, the Sturm variation of the signs function, is constant in every one of these open intervals. So the only time this can change is when you cross a point in lambda, where you go from a number which is less than a 0 of one of the GIs to a number which is greater than a 0 of one of the GIs. And let's see, what else can we say? Well, so if at one of these points GI, one of these numbers d and lambda, if GI of d is different from 0, then the sign of GI of x, so let's say GI of d is positive at d, the function is continuous. So it's positive a little to the left and it's a positive a little to the right, which means it's positive in the whole interval to the left and it's positive in the whole interval to the right. So the sign is constant at d and for all x in the two adjacent subintervals. But suppose that this d is in lambda and it's a 0 of the polynomial gk. But we just proved that no two not for G0, but for k between 1 and r minus 1. GR is identically 1. So we know that no two consecutive terms in this sequence are 0. We just proved that. So GK is 0 at D, but GK minus 1 and GK plus 1 are both non-zero. And now here is the point. So this is like a little piece of magic. Someone was brilliant, right? Sturm was brilliant. Instead of doing the usual division algorithm, he made this a minus sign. And if this is a minus sign, if you evaluate this at D, GK of D is 0. So this is 0. GK minus 1 of D is minus GK plus 1 of D. That means these numbers, GK minus 1 of, well, this means GK minus 1 of D is minus GK plus 1. That means they have opposite signs. I mean, that really is, if you like, the secret of Sturms Theorem. This stupid thing of putting in a minus sign, right? I mean, what a dumb idea, but it's brilliant, right? That's what does it. So these have opposite signs, And so let's look at this three-term sequence. GK minus 1 of x, GK of x, GK plus 1 of x. So at D, this is 0, and this is positive or negative. If this is positive, this is negative. If this is negative, this is positive. So what are the number of sign changes among these three terms? Well, you have to think about this for a second. Let's say this is positive and this is negative. How many sign changes can there be as you go from here to here and here to here? If this is positive, 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 negative, a sign change. If this is negative, positive, negative, negative, a sign change. If this is 0, positive, 0, negative, the 0 doesn't count, a sign change. So no matter what this is, the number of sign changes here is 1. So there's exactly 1 sign change for each GK. So this variation of signs function, as you move across this D, which is a 0 of one of my functions in the sequence, but not of the original f, the number of sign changes doesn't change. This is whatever this is to the left is exactly what it is to the right. Right? I mean, that's the part that maybe one has to think about a little bit, but that really is this lovely observation. And so what this says is that if you take the sequence G1 up to GR, so this is not the whole Sturm sequence, I'm leaving out G0, but the number of sign changes in this is constant as X varies from A to B. All right, that is, so the only possible sign changes occur at G0, from G0 to G1. And so suppose here's G0 of X, and D is a simple, so let's say G is 0, D is 0. And we eliminated all multiple roots. So D is a simple root of G0. So G0 is X minus D times G of X, and G of D0 is different from 0. And this is G1. And well, I mean, here's an argument. It's not, I mean, this is the argument. There's 1 sign change, right? You see, look, here's G0, here's G1. So if X is to the right, if X is bigger than D, this is positive and this is positive. So let's see. So G0 of D is 0. G1 of D is the same as the sign of G of D. If you look at X to the right of D, this is X minus D is positive. G0 of X has the same sign as G0 of D. And the same with G1. But if you look at X to the left, this is negative. This is going to have the opposite. This is going to have the opposite sign. This sign isn't going to change. So the second part of Sturm's theorem, the crux of this is X minus D is positive if X is bigger than D, and X minus D is negative if X is less than D. And that's what gives us the sign change whenever you have a simple root. Now, I have 100% certainty that what I just said is incomprehensible, but that's why God invented books where the stuff's written down so you can look at it and you don't have to try to figure it out in 2 minutes. But the number of sign changes of the sequence is constant from A to B, that this variation of signs function decreases by 1 as X moves, I don't know why it says increases, as X moves from left, as X increases from left to right over 0 of f of X. So I have this function and I start at A, and I just see how it varies as you move from A to B. And every time you hit a 0, so this has some number, whatever it might be. And every time you hit a 0 of f, you have a sign variation. And by the time you get to B, you have one increase in the value for every zero. And that, Mirabile D2, as we say, for those of you who went to Boston Latin, is the proof of Sturms Theorem. So that's what I wanted to say. Now, what I still have to figure out, I still have to figure everything out. That is, I have no idea how to prove Tarski's theorem or Seidenberg's theorem. And the first step is to figure out, to understand, or even to find Tarski's generalization of Sturm's theorem, because he needs a slightly stronger form to have the theorem work. And see, what Tarski does is he starts with polynomials and inequalities in one variable, and somehow gets from that to several variables using Sturm's theorem. Seidenberg, who is an algebraic geometer by training, and but this is 1954, so this is fairly early. So in 1954, Grothendieck was not quite a kid, but he was sort of early on in his career. And if you were an algebraic geometer, the Bible was Andre Wei's book on foundations of algebraic geometry. And there are tools from Wei that Seidenberg uses. In any case, I am, for whatever reason, interested in this at the moment, but I would be very, 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 very happy if someone could spend some time looking at one or the other of these papers and be willing to talk about part of it. But obviously, no one has to, obviously.
That's a nice presentation you gave.
Well, thank you. I thought it was incoherent, but
No, the main ideas were there.
well, the main ideas of some things, but maybe of Sturm, but not of Tarski. And that's really what I want to get to.